All right, so now the kind of big crux of all of this is that we want to slowly move into a world of not having to do all of this stuff by hand, because doing this all by hand is somewhat terrible, but we need some more information about the recursive structure that's actually taking shape. So the next couple of slides are me writing out some chicken scratch about trying to see this recursion actually take shape. And then once we have that whole procedure, we can actually go crazy with it and actually try to implement this particular object. So in this case, I'm going to try to keep things somewhat structured with symbols, but I'm going to be terminating this process at arbitrary stopping points. So what I'm going to do is I'm going to be given some pair of numbers a and b, which in this case I'm going to convert the a to being an r0 and the b to an r1. And you can see that if I run this process, I did my division one time, so that was my first division, and then I had my second division, and this process terminated after one stage. So if you do the back substitution, you only have to work with this equation. And it's pretty nice to work with. You just move everything over, so it says R2 is equal to R0 minus Q1 multiplied by R1. It's the situation that if you were to, I don't know, take a pair of numbers, let's say 11, and if you ran it with the pair 5, this thing terminates in one step because you have 11 is equal to 2 times 5 plus 1. So you can easily solve for 1. It's equal to 11 minus 2 times 5. So that's all that's saying, but in fancier symbols and things like that as well. So what you can see is that that whole process stops after one step. So we know the coefficient in front of the a term. So if I put that back as an a, and if I put this one back as a b, my coefficient in front of the a simply happens to be a 1, and my coefficient in front of the b ends up being that negative times the quotient, which is exactly what we see right here. This is 1 times an 11 minus 2 times a 5. So I'm going to give these things fancy names. That thing in front of the R0 I'm going to call a capital Q1, which is in this case identified as a 1. On the other side, the thing in front of the R1 I'm going to call a P1. And I'm not currently worrying about that negative sign. That's something that I will fix later. And you can see the negatives kind of come into play when you run this back substitution, is that the number of back substitutions that you do is essentially going to keep track of the sign flips. Because if this was negative, you can see that distributing the negative turned it positive. But then the next time when I distribute, it's going to become negative, so it's going to constantly flip back and forth, back and forth, back and forth, back and forth. So right now I'm not going to worry about that stuff, but it's going to be something that I will have to fix eventually. So this Q1, P1, that becomes the starting place for my recursion. What I want to see is what's going to happen if my process terminates after another round. So in this case, same exact stuff, except for I required it to run one additional step. So I had my original pair of A and B. It generated a remainder R2. And then I did the division one more time to generate an R3, which I didn't have in this case. But now I have an R3. And then it terminated after the next step. So it fired off a 0 at what would have been R4 in this case. So now if you do the back substitution, you're going to start right here. So R3 is going to equal R1 minus Q2 times R2. And then you're going to do the back substitution with the R2 as being R0 minus Q1 times R1. And at this point in time, I'm going to distribute the Q2 into that first R0 term, and it's going to get distributed over here. Again, here's that double negative sign world, so it's going to be negative, negative, which turns into a positive. Like I said, we'll deal with that negative stuff later, but for right now, that's where the sign changes are going to occur. I'm going to regroup things, so putting the R0 stuff out in front, and then I'm going to move all the R1 stuff to the back. What I want to think about is that this thing essentially required 2 of these divisions that did not generate a 0 remainder. So I want to think about the weight in front of this R0 as being like a Q2. If the previous stage was called a Q1, this is a Q2, and this should then be a P2. So what ends up happening is that my Q1 was a 1. My Q2, you can see, is the little Q2, that quotient that occurred on that second division. So what's actually going to end up happening is that Q2 is going to be recursively defined by taking Q2 multiplied by Q1, which in this case is just Q2 times 1, which is Q2, little Q2. On the other side, it becomes a little bit more interesting. This P value has a little bit more stuff going on. My P1 I remember as being this little Q1, that first quotient that occurred. My P2 then becomes Q2 times Q1 plus a 1. If I remember what this Q1 happens to be, that's my P1, so I see this recursive structure of being the quotient at level 2 multiplied by the previous P1, and then I'm going to add a 1 to it. And that becomes the starting place that we're going to be able to generate the next term over and over and over again. There are always going to be these combinations of taking that current level's little quotient, multiplied by the previous capital P or capital Q, and then there's going to be a couple little corrector terms that come into play as well. So if I want to see some terrible notation come into play, is what happens when I run this one more stage. So I do my first division at round 1, then the second division at round 2, then the third division at round 3, and then finally at round 4, I found my 0 remainder. So what's going to happen is that it requires a few back substitutions, but it's the exact same process that we saw before, is that I have this R4, so right here, back substituted with R2s and R3s. Then I'm going to back substitute what that R3 happens to be, introducing that purple gunk. Do a little bit of cleanup, moving all of those R2s to the very end. And then at my very last stage, I'm going to take that R2 and then substitute it with some R0s and Q1s and things like that. And you end up getting this big old structure take shape. And the question becomes is, how does that connect to our previous stages of Q2 and P2? And it's pretty cute. What ends up happening is that if we look at this particular stage, I have my Q1, which was a 1. My Q2 is then achieved by taking the previous quotient, that quotient Q2, multiplied by that previous Q1, which in this case is just a Q2. And then at this next bit, you can see that I have Q3, so the current quotient, multiplied by the previous quotient, plus a 1. Well, in this case, what that simply ends up being is it becomes Q3, the current quotient. The previous quotient is actually embedded as this capital Q2, and then that plus 1 is actually the Q1. So that's the general shape that's going to happen for the Q's once that index is above level 3. And the exact same thing is going to happen for the P's as well. So the P's have a little advantage in that they're both recursively defined essentially the same way, except for my initial terms are offset. So my P started off with a Q value already. So my P1 was Q1. My P2, you can see, was my Q2 times Q1. So those current quotient value, previous quotient value, plus 1, which is then functionally my Q2 times my previous P1 plus 1. So my next stage, P3, if I'm thinking about it, should be a Q3, the current quotient, multiplied by the previous P2 plus the one before it. So I get this general shape, which is the same shape that I saw for my Q. It's just they're offset. Like I said, the P's have a slight advantage as to what's actually occurring. And hopefully some alarms of efficiency are starting to come off, is that these things can actually be computed more or less the exact same time, because once you have P's, you actually technically know what the Q's are. So you'll see a whole bunch of that as we go, but they should hopefully be firing off all kinds of things of being like, hey, I know what's about to happen. I know what's about to happen. And if you want to verify that that actually is correct, if you substitute what P2 happens to be, and you substitute what P1 happens to be, you get this whole giant mess of that coefficient in front of that R1 value. And that's it. So the Euclidean algorithm, as terrible as it seems to do by hand, is actually achieved pretty quickly through this nice recursive process, is that we have to keep track of the quotients at each level, and we got to keep track of some of those remainders. Well, you're already keeping track of the remainders to do the GCD, and now you just care about what the quotient is at any particular stage. So that gives us this very nice formula or procedure for actually generating these little solutions U and V. And that's exactly what we have. I have P1, this capital P1, which is identified as being a little q1, my capital Q1, which is identified initially as being a 1, because that's what we took it to be back here. And then I create my Q2 and my P2, and then after I is larger than 3, then I use this nice formula of take the current quotient multiplied by the previous P plus 2 stages before it. And it's the exact same for the P and the Q. The last little thing that we need to record is those negative signs. And that's the thing that we kind of said, oh, we'll deal with it later in this case, is that you can see that at level 3 in this case, my final solution of having this horrible guts equaling my final R4 value, what it ended up firing is it ended up firing off a -1. Whereas in the level 2 one, that term in front of it was positive, and then my original one back here had a negative. So you can see that they flip-flop depending on how many stages my division actually took. If my process terminated with a 0 at level 2, you can see that that second one has to be negative. Whereas if I identified my 0 at level 3, that became positive. And if I identified my 0 at level 4, it became negative. So that's where that last little corrector term in this procedure is keeping track of, is that I have my sequence of quotients, which are Q1 through Qt. So T is recording how many steps I had to do. And then I'm going to fix that little term with the P's by stuffing a -1 to the T plus 1. And then on the Q1, it's going to be 1 less, so that these two things are always going to be flip-flopped negative signs of each other. So I'd recommend going back and seeing if that holds true for these things, is that you can identify where this process terminated and then what type of negative actually ended up occurring. So in this case, we saw that it terminated after 4 stages, so my T value is a 4. So if I go back, in this case, my 4 plus 1 is 5, so that -1 to the 5 is actually going to fire off a -1. The idea is that if I multiply -1 an odd number of times, it's going to turn out to be negative. Whereas if I take -1 multiplied by an even number of times, it ends up churning out a positive. So with this, we can actually identify a fairly simple modification to our Euclidean algorithm. We have the same exact block of stuff that I had before. That I just literally copy and pasted, except for in this case, I implemented an extra stage where I'm constructing these PIs and QIs. And at this point in time, it's fairly inefficient because I'm keeping track of way too much information, but it does generate a nice solution. So it does work, it's just not great. So in this case on D2L, you're going to see an actual implementation of this done in Sage. It's the same code I had before, except for now I added in this little extra bit, which is pretty nice to actually see take shape. And in the next video, I'll probably actually end up going through it as well as talking about how you can do this by hand, because it's actually a pretty simple thing to do by hand.